Two polished metal plates a hair apart get pulled together. Nothing touches them, yet a measurable force appears from nowhere. Quantum vacuum fluctuations create a tiny pressure called the Casimir force. Here is the immediate takeaway: space itself can push on matter, not with molecules or wind, but with how emptiness is structured. Change the gap slightly, and the force changes instantly. Engineers have measured it with micronewton sensitivity inside clean chambers. That pressure comes from allowed electromagnetic modes between the plates. Fewer modes fit inside, so outside pressure wins and plates attract. So empty space is not passive background, it sets outcomes. Starlight skims past a massive galaxy cluster, then bends like water. That bend is gravitational lensing, light following curved spacetime geometry. It lets us map invisible mass and test gravity with precision. Space around heavy objects is curved, so straightest paths become arcs. Photons still move at light speed, but their direction keeps changing. Clock rates shift near mass, so the travel time also shifts. The image you see is the path of least time. Astronomers watch multiple images of one quasar flicker with delays. Those delays run hours to weeks, set by geometry alone. Einstein rings often span arcseconds, yet they reveal dark matter. A single arcsecond is a coin on kilometers, seen far away. With careful modeling, we weigh clusters without touching them at all. The light never collides with the mass. It obeys space's shape. Rule of thumb: geometry decides the options, forces decide the choices. So curved space guides light, and outcomes shift without contact. Picture a dark lab bench with two electron beams skirting a coil. The magnetic field stays bottled inside the coil's metal shell. Still, the interference fringes slide, as if nudged by a ghost. That ghost is the Aharonov Bohm effect, phase from electromagnetic potential. It matters because potentials shape quantum phases, which set measurable probabilities. The vector potential adds phase along each path, even where fields vanish. Interference depends on the phase difference, so the pattern moves. The loop integral of potential equals enclosed magnetic flux times charge. Gauge choices change descriptions, but the loop's value stays physical. When enclosed flux reaches half a flux quantum, fringes shift half period. One flux quantum is about 4 times 10 to the power of -15 Weber. Experiments see clean shifts with shielded coils and careful alignment. No electron touches the field region, yet outcomes reconfigure crisply. Example in real terms: shifting phase redirects where electrons actually land. Net result: space's potentials steer results, even when forces are absent. Inside a mirrored cavity, faint standing waves hum like trapped fireflies. Boundary shapes decide which waves can live and which cannot. That is what boundary conditions mean in physics: allowed patterns only. That matters since modes set energy density, pressure, and emission rates. Walls force nodes at specific spots, so only certain wavelengths fit. Fewer modes inside means lower vacuum energy than outside. The difference pulls plates together. That is the Casimir attraction. For a 100 nanometer gap, pressure is roughly 10 pascals. Push the gap to 10 nanometers, and pressure jumps near atmospheres. Emitters inside a tuned cavity can glow faster by Purcell enhancement. Factors of 10 are common in compact microwave or optical resonators. Designers use shapes to boost desired modes and kill unwanted ones. One sentence recap: boundaries edit the menu, and physics orders differently. So geometry of empty regions changes forces without any touching. A single photon walks toward two slits, grinning at the options. With both slits open, the screen paints crisp, bright, and dark bands. That picture is interference, amplitudes adding or canceling across space. That matters as available paths determine probabilities, even unused ones. Each path carries a phase, so two paths can reinforce or erase. Tag one path with information and the bands wash into fog. Close a slit meters away and nearby hit locations reshuffle. The photon never meets your hand at the distant shutter. Still, the distribution changes because the space of options changed. Example in real terms: red light at 650 nanometers and 1 meter. With slits half a millimeter apart, fringe spacing is about 1.3 millimeters. You can measure that shift with a ruler and a cheap laser. Common mistake is thinking the photon splits like a tiny marble. Instead, the wave function explores roots, and probabilities show the result. Bottom line: changing paths changes outcomes, without local nudges at impact. Two entangled photons leave a crystal, then fly to distant stations. Detectors click in neighborhoods, separated by city blocks or mountains. The outcomes match in patterns that beat classical limits convincingly. That pairing is quantum entanglement, shared states across separate locations. Stakes are high because this underpins quantum networks and secure keys. Measurements remain random locally, but correlations follow tight quantum rules. Bell tests compare patterns and rule out hidden classical instructions. Teams arranged settings so choices are space-like, closing timing loopholes. No messages cross faster than light, statistics still demand a link. Correlation strength often exceeds 80% visibility in clean experiments. The MISHIS satellite shared entanglement over 1,200 kilometers through thin air. Fiber networks already span over 100 kilometers with entangled pairs. A single twist of a polarizer flips joint statistics immediately, yet no one can signal because each side sees fair coin tosses. So joint structure in space of states constrains outcomes minus forces. Pan across a patterned chip where repeating holes herd light like cattle. Symmetry in space dictates what can move and what cannot. That principle ties symmetry to conservation, locking quantities into place. Break a symmetry and you unlock new behaviors and restrictions. Translational symmetry gives momentum conservation in free, uniform space. A wall steals that symmetry, so momentum perpendicular can change. Rotational symmetry guards angular momentum. Patterned crystals relax parts of it. In periodic media, waves form block modes with allowed energy bands. Gaps open where waves cannot live, no matter the push. Photonic crystals can block 10% frequency windows with ease. The same logic shapes electrons, phonons, and even matter waves. Example in real terms, bend a waveguide gently and stop leakage. One sentence recap, shape the symmetry, and you shape the outcomes. Net result, space's rule set decides what can happen before forces act. Zoom into a coiled fiber spool, glowing faintly under a laser. Path shape now writes a phase, even when fields feel constant. That extra piece is geometric phase, set by the root's contour. That pays off as geometry gives noise-resistant knobs for precision sensing. As parameters trace a loop, state vectors twist and come home different. The phase depends on enclosed area on an abstract sphere. In optics, polarization scribbles angles on that sphere, then shifts color. Fiber gyroscopes use the Sagnac effect, rotation changing travel time. Two beams race both ways, and the rotating loop favors one. With 1 kilometer of fiber, microradian phase shifts become measurable. Commercial gyros resolve around 1 degree per hour, improving with length. Geometric control also guides qubits, with paths that cancel noise. Quick tests change the loop area and the phase scales linearly. So path geometry alone can steer outcomes, with nothing pushing directly. A cavernous hall glitters with mirrors, vacuum pipes, and chilled chips. The shared theme is simple: space has become a design variable. That sentence means fields, geometry, and timing are knobs you can turn. Stakes are practical, better sensors, clocks, chips, and secure links. Engineers quiet vacuum noise with shields, cavities, and filtered modes. They route paths to harvest constructive phases and cancel destructive ones. Survey teams use lensing maps to weigh clusters and track growth. GPS works because we correct about 38 microseconds of relativity daily. That correction keeps positions within meters instead of drifting kilometers. LIGO listens for strains near 10 to the power of minus 21. Atom interferometers read gravity gradients in parts per billion differences. Superconducting qubits last longer in 3D cavities, often 10 times longer. Example in real terms, layout alone can boost sensitivity without extra power. So treating space as programmable makes outcomes predictable without direct contact. Empty space pushed plates together at the start, remember that moment. We chased how geometry, potentials, and paths can steer results. The thread stayed constant, nothing touched, outcomes changed anyway. That is the surprising part, yet the math stays consistent. Fields live everywhere and boundaries edit which notes can play. Curved spacetime guides light, while phases tally every possible route. Entanglement sets joint rules, even as signals stay causal and local. What to remember, space is not scenery, it is part of the machine. If this clicked, stick around for more clear, calm physics stories. One thoughtful share or sub helps and it tells me to continue. So the picture is tidy, shape space wisely, and outcomes follow.